Hi everyone, my name's Mike. I'm a partner with a company called Pragma. We help software organizations with development, test, and operations automation. So continuous delivery and DevOps, basically. So today I want to talk about build systems. I've spent a lot of time with build systems. A lot of my professional background is in embedded systems. The very first project I worked on after university was actually, it was an embedded system, a control loop for a product that was to go down deep down into oil reservoirs. And on that project, my first experience of professional software development, the build system was actually an IDE. And I pressed the build button on the IDE, and that was the software I shipped to the customers that went down in oil reservoirs. I shudder when I think about it now, but there was absolutely no process, no control over anything that came out of that. There was no reproducibility. Definitely, it was all based on whatever configuration and environment I happened to have on my laptop. Thankfully, I learned a few things since then, but slowly, industries have changed. The second project I was involved on was much, much better. We had a version control system, but because we were a very, very big company, no version control system on the planet was good enough for us. We had to build our own. And guess what? We also built our own configuration management system and our own build tools. So that was an interesting experience too. But the thing is, in that case, there was some real business drivers for having made those decisions. The build systems back then, you didn't have a lot of choice other than make. And make was, in essence, very, very slow if you had a very, very big code base. And back in those days, builds could take more than a day. So we had built special build tools to enable us to have what was called baseline builds, where we built only the things that were different between us and what the servers had built overnight. And nowadays, more and more of my work is working with embedded systems as well still, but we're starting to use things like Docker and so on to capture the environment, but we're also using tools like Artifactory or Nexus, other kinds of artifact management tools for the binaries. And where the build kind of fits into this world is kind of tricky. We've started exploring different tools to use. More and more often we're using Gradle, but then suddenly I kind of came to the realization that maybe it's time to spin up the helicopter. Maybe there's more out there than meets the eye. So we started a project internally in the company to start to look systematically at all the native build systems out there, try them out, give them a go, and evaluate them against the others and see what they're good for. So this is still very much a work in progress, but I want to share with you the things that we've been looking at and what we've found. So yes, why do we need an alternative to make? There's actually nothing wrong with make. Make is actually very good at what it's designed for. The thing is that the context of software development has changed a lot since make was designed. Yes, we need dependency analysis to be able to figure out what to build, but there's much, much more than that we need. So a lot of I'd say that there's two main drivers for picking a tool other than a very simple make or CMake or one of these variants of tools. One is that you want to interact with artifact management systems, packaging systems, and so on. You might want to resolve dependencies from some binary repository. You might want to produce versioned artifacts. You might want to interact with the world in a different way. It's not all just happening on your laptop these days. The other main driver is coming from organizations with very large code bases, because they have many more challenges. So optimizing that build throughput is very, very important for them. Developer efficiency in large enough organizations is a big driver. So they're looking to do things like either be very, very smart about what is built, basically only building what absolutely needs to be built, and being very strict about package management so that you can avoid building things. And then the other side is, if you have a very, very good understanding of the dependency graph, then you can be much more aggressive in parallelism. So that's really the two main drivers, artifact management systems and the builds. Now, there's another desirable feature that I would like to have if I was going to pick a tool, and that is a strong community. I really want not to be picking a tool that has that's a dead end, because our build systems last for a long time. We really don't want them to be very clever. We don't really want to have to update or patch them. We want to be able to rely on them like we can rely on Make. So we want to have a very, very strong user base, and we want it to be open source so that if there's something we want to add to it, we have a chance of doing so. Good. That being said, so far we've had a look at 5 contenders to make. We're using, like I mentioned, we're using a lot of Gradle in our company at the moment, and that's very interesting. But there's many other choices out there. We've looked at Conan, we've looked at Basil, we've looked at SCons, and we've looked at Buck. So there's many other options out there. There's Ninja, there's Pants. We haven't gotten through the whole list yet, but this is a work in progress, and it's very interesting how these tools, what they're similar and how they're different. Out of interest, is anyone using any of these tools at the moment? What are you using? It's okay. Conan, okay, very good. So I'm going to start with Scones because I think it's probably the one closest to Make and furthest away from what I'd like to see and something to replace Make. Maybe that's related. It's an open source tool. It came out of, I believe, a company called Software Carpentry or something. That's where it got its name. And it's maintained by the community at this stage. It's, I think, around 15 years old, so it's not, I would say, it's not a very modern alternative to Make in that sense, but still much younger than Make is. So what does it look like? I mean, if you ask me, when you start to write your build files with Scones, it starts to look pretty ugly. It's basically Python. You can actually write Python. This is actual Python. And it looks very imperative. It does build a model of dependencies much like Make, so that's where it is similar, but it's not super intuitive to figure out what your build looks like through going through this, at least in my eyes. So some of the features it has, the build files are Python scripts, so if you know Python, you have a strong Python culture in your organization, this might be a good place to start. It is better than Make at doing parallel builds. It has some automated dependency discovery built in. I'm not actually sure if that can be trusted on larger projects. I'm not sure in terms of incremental builds and so on if you can really trust it, but it is there. And it feels very Make-like. So it's not a big leap to learn. It's not a challenge. On the development environment, it has some implications. It does mean that you will have to have Python, and it's not so declarative. So this is a common tool you'll find in code bases that are around 10 years old, or maybe this was a tool that was chosen 10 years ago. This is something that was a good choice 10 years ago, and that was its time for adoption. But I think now that we have much stronger contenders for tools in this space. Okay, the next tool is the one I probably know the most about, because it's the one I have actual project experience with, and it's called Gradle. It is open source, but there is a company behind it also, Gradle. So Gradle, in essence, is based on Groovy. It's a DSL over Groovy. So it has a domain-specific language that you can create a model of your build in, and it can be quite rich. It has elements of, if you're familiar with tools like Ant, where you have this idea of concept of tasks. So I think it, at least initially, one of its goals was to try and kill Ant and Maven, but keep some of the concepts. So for people, especially in the Java world who are familiar with that, it kept a lot of those fundamental concepts, but brought the build system into a programming language rather than file format, because those were the weaknesses with Maven and Ant, is that you were defining everything in XML. So if you wanted to do something a bit more clever, it was really hard. You had to break out of the build definition and start to execute scripts. So they found that this was what they were trying to achieve here. The native build support came later. A few years ago, the native build support wasn't as rich as it is today, and it's much, much better now. But also, what is very common is to use Gradle as a wrapper to your build system. So if you're already using make or whatever your build system actually is, you can call into that to perform the build, but use Gradle for the other aspects of the build, such as the packaging, dealing with the binary package repositories and so on. So it's not a one or the other thing. Quite often these are mixed together. And it's especially useful if you're making embedded systems where you've got very integrated development tools, where you would like to, like for instance, the tools generate the make files, and you really would like to use those make files. But on the other hand, you would like to have some tooling around dealing with packaging. So this is a very common solution there. Some of the features, Gradle does have a very, very large user base. Most of them are not doing native software of any kind. Most of it is Java people. But there are some very large projects using Gradle, and Android has very good support. The Android community works together with Gradle to make sure Gradle works with Android. It has quite good native support. It has a DSL for describing the typical C and C++ concepts that you would want to define in your build, like shared libraries, static libraries, executables, and so on. And like I mentioned, you can use it to wrap your actual build if you would rather keep make as your build commands. It has a large plugin ecosystem, and this is actually very useful. Being able to create Gradle plugins, reusable plugins that you can use in different kind of build contexts is very, very useful in some instances. So in that case, it makes it very easy to extend the language. It's got support for incremental, parallel, and continuous builds. It does, at its core, since it's coming with this Java heritage, have very strong dependency management built in. It's very much influenced by Maven, and you can use it to talk to Maven or Ivy or Artifactory or any of these typical binary repositories. One of the nice things about Gradle is that the dependencies you need to be able to run it is the JVM. And what you do is you put in a couple of wrapper files into your source control. So those wrapper files are only like a bootstrap for downloading the version of Gradle that you're supposed to have in that build system. So in that sense, you don't need to really control very much of the environment. You just need to have a JVM, and the rest will kind of take care of itself. It has support for assembler, C, C++, Objective-C, C++. So it has a lot of the features you need out of the bat, and it's probably the one of the tools that is good at both artifact management and build. It's the one that's come the furthest there, I think. Maybe Conan is an exception because it really is designed with that in mind. So some of the implications about Gradle is that you need the JVM, like I said, and that's not a big deal. But really what is a bit of a big step for most is that you kind of need to learn Groovy. You can learn Gradle by going through the docs, and the docs are quite extensive. But to really understand what the docs are telling you, you have to understand Groovy. You have to understand the whole concepts behind the language. Otherwise, you end up just typing in a bunch of stuff into your editor and praying that that's the right thing. So it's if you are going to pick up Gradle, it's really worth taking the time to learn it properly. So the next one I want to talk about is Basil. Basil's coming out of Google. It's not the actual build tool that they use in Google, much like Kubernetes isn't the actual runtime for containers that Google uses. But like Kubernetes being influenced by what they learned from Borg, Bazel is exactly influenced from what they learned inside Google with their build system. So what does it look like? Well, it's actually quite simple. You define rules, and you have different types of rules, but because it's really set up for C, C++, it's very, very natural. You don't have to tell it a lot of things to be able to build your software. You say, okay, this is a C library or C++ library. Here's where to get the sources, please make it happen. I mean, you can tell it more things. You can give it more instructions if you need to go further in your definition. But in general, this is all you need to do to produce your artifact. And here you have an example of fetching the binaries from the internet. And here we're downloading the Google test framework and taking in the dependency on a fixed SHA. So we will be sure that the version of the Google test library that we're using, everybody is using the same. So one nice feature is it's really designed based on what Google have learned about making large build systems. So the design is really well suited for large code bases. It has a built-in query language, which again is very useful because normally what happens in big build systems is you can never figure out what happened. Why doesn't it pick up that dependency? Why does it pick up that dependency? Why is it rebuilding that when I change that? Understanding these things is actually quite a challenge. So Bazel has a built-in query language you can ask it these questions. Much like most things with Google, it has a defined style guide, so there is a right way to write a Bazel file as well. So in general, there's not 100 different styles on the internet. Generally, people follow a convention that's consistent, so it makes it easier to learn. There are some new concepts in it. You have this concept of a workspace. You have concepts of packages and labels. So you do need to take the time to understand it's not just figuring out how to call the compiler. There's more to it than that, but the concepts are quite clear as well, and there's really, really good documentation. So it's quite easy to get started with Bazel. It has support for nice things like transitive includes. So if you pull in a library that also pulls in a library, and that transitive include you need, it will sort that out for you. The other thing it has is, oh no, sorry, I'm mixing this up with Buck. It doesn't have what I was about to tell you. But it has support for incremental and parallel builds, and it's really, really designed for speed. Like, how fast can we build this thing? And it's about making very, very clear definitions of inputs and outputs of rules. One of the things that is both good and bad about Bazel is that it's in beta. So the good thing is Google are honest enough to tell you that it's not 1.0 yet, which maybe some other tools are not so good at telling you these things. We've especially found some of these tools have got very poor documentation, or the documentation is out of date, or they changed things, but there are some things that could still change, but there is a roadmap online, and it's very, very close to becoming 1.0. So I'm actually quite impressed with Bazel, and I'm going to keep an eye on this one. The next one I want to talk about is Conan. This was made. It was an open source project to begin with, but I believe that the group that was developing it were acquired by JFrog, the people who make the Artifactory artifact management system. So Conan is, it looks like this. It's based on Python. So you create a Conan file and you specify a bunch of things and about how to do the build and packaging and so on. But there's a lot more to it than just build. It has this kind of very, very strong influence from the world of package management and dealing with, it's actually a distributed package management system. So one of the special things about Conan is that it is not a build system. It doesn't do build. It defers the build to something else, like CMake or Visual Studio or whatever your build system happens to be. It's not really concerned with the build system. So it's a bit of a special case here. And to call it a replacement for Make is not really telling the truth. It's not. It's orthogonal to the build system. So it claims to be compatible with any build system too, and I don't see any reason why it shouldn't be. But where it's really doing its thing is it's a decentralized package manager, and that means much of the design is influenced by Git. So they have this idea of remotes and the idea that you should be able to fetch and publish to different remotes, just like you could do with commits in Git. Obviously, with them being acquired by Artifactory or JFrog, they have very good Artifactory integration. There's a client-server architecture. So much like Git, actually, the idea is that you push and pull from a package server. Sorry. There's also support for building offline, so you don't need to be connected to the server. So that's kind of where some of this other Git influences are coming from. And yes. It does require a build system, so it's never going to, if you're building with Make, then it's probably going to, you're going to continue building with Make. You also need Python. One of the things that's a bit frustrating just now is that the documentation is quite slim and it's example-based, but many of the examples in the documentation are out of date, and I think that they're changing a lot in their design just now, so it's a little bit hard to know exactly what you're supposed to do and why it's chosen this way or that way. On a given page. So I think Conan has a future, and I think it's very interesting. I think it's got some really interesting concepts, but I don't think it's ready for production use just yet. And then the last one I'm going to talk about is a tool called Buck. Buck is coming from Facebook, but that's not actually quite true, because the people in Facebook that built Buck are actually ex-Googlers. So they were very much influenced by the way the Google build system was. So Buck and Basil, if you step back a bit and squint your eyes, they look kind of the same. There are some differences though, but you can see the file format looks quite similar. There are some important differences, but it does look kind of similar. So just like Basil, Buck is used in production in a very large company making a lot of builds. It's very similar to Basil, and it's focused again on performance and reproducibility. The idea is that you should have known dependencies, and the inputs and outputs should be known so that if something changes, I know what to build. And it's really focusing on this correctness principle. There is strong support for Android, so if you're making Android applications, then this is probably something you might consider. It has this thing for it's like a design for include collision. So basically when you include a dependency or a package, what it does is it gives those header files its own directory. So you have to be explicit on which utils.h you're using. You can't just include utils.h and have all the other packages on the include path, because you really don't know which one you're going to get. So what they do is they make sure that they're kind of given their own path, and you have to be explicit about which one you want. And that's a good thing in my opinion. I think it's quite useful. And it has also this concept of private headers. So when you're publishing a package, you can say, okay, well, these are my public headers and these are my private headers. So don't only export the public ones. It runs on the JDK and it requires Python. I think most of these tools seem to be using the JDK or Python or both. But they're all actually really smart about how they use the JDK as well. They have the JDK running all the time as an agent in some ways. So you don't have to wait for the JVM to start every time you run a build. So these builds can be very, very fast. Okay, so that was the 5 build tools I've been looking at so far, but there's many more out there. We're not done yet, and if there's any build tools you would like us to look into, or you think that we should look into, I'd really love to hear more about it. We're trying to build some kind of side-by-side comparison of all these different tools, trying to make some, not necessarily a feature matrix, but at least one place where we can see them all side by side, where they go, where they don't go, and understanding all the places, all the different features they have. And we also have set up a bunch of, basically a repo for each of these build tools, and we've implemented a project, a build system for a project with the tool. Created Docker images to contain the environment, so we can all try and share the tool's environments and set up CI/CD pipelines for them. So in all these cases, this is all open source, and if you're interested in getting involved, please just jump in, send us a pull request, create issues if we've got something wrong, if you want to add something. If this is interesting to you, jump in. That's all I want to say. So, thank you. Yes?